Today we will not get to a large part of your assignment, but it is the beginning of a 3-day topic. 3-day topic, 3-day topic. You need to be completely locked in or you're going to get lost. Yep. It is time to move from approximations to exact. It's time to move from approximations to exact. Are we ready? We have the function f of x. It's bounding this area from A to B. The way that we represent that using calculus is something called the definite integral. And it looks like this. The definite integral from A to B of f of x, and we attach a dx. I will rewrite it so you can see it again. The definite integral from A to B represents the area bounded from A to B underneath the function and the x-axis. We want to compute that exactly today. You don't know what that means. We're going to teach you a way to look at that in a little while, but first we're going to express it as the infinite limit of rectangles. So we're going to push the rectangles from 1 to 2 to 4 to 8. We're going to push it all the way to infinity. This is a mind-blowing day. We're going to help you experience it along the way. So, looks like this. The limit as n goes to infinity. And remember, when we added up all these rectangles, our formula was to take the width times the sum of the heights. Agreed? So, I'm not going to focus on the width yet. I'm going to focus on the sum of the heights. There was a symbol that we learned last year. Hopefully you can remember this a little bit, but we used this symbol. Do you remember sigma notation a little bit? It meant sum. This meant what we started with. We're going to start with I is equal to 1. We're going to start with rectangle number 1. We're going to push it to how many rectangles? An infinite number of rectangles. The sum of what? The sum of the heights. Remember how we found the heights? We plug the x values into the function. So we take x of I and we plug it into the function. So this says the sum of the heights of the rectangles. How many rectangles are there? There's an infinite number. And then we need to multiply it by the width. And the width is delta x. Delta is, the Greek letter for delta is a triangle. That's the capital delta. The small delta is like that. We've already talked about small delta before, right? So this is what we want to accomplish today. It is going to be challenging today. Tomorrow it's going to make more sense. And by Friday, you'll be like, wow, this is actually easy now, though it was tough when we began. Going to help you understand how to get your frame of mind around this. First, suppose you're finding the area under x squared, and you're going to bound it from 0 to 4. Talk with your friend. If you're finding the area of 8 rectangles, what is the width of each rectangle? 15 seconds, go. Five, four, three, two, one. What's the width of each rectangle? 1/2. How do you get that? You took 4 minus 0 and you divided by 8. That's the width of each rectangle. Now, we are going to go back to right hand sums. If you are going to have a width of 1/2 and you're finding the area of rectangles, what x values do you evaluate the heights? So I start 0 and I go over to 1/2 and then to 1 and then 3/2 and 2, 5/2 and to 3, 7/2 and to 4. That's kind of the diagram that we map out, right? So if I'm doing right hand, for what values do I evaluate the height? Which one do I start with? Do I start with 0 or 1/2? I start with 1/2. And I grab all the ones the rest of the way over. Agreed? Okay. So I'm just going to circle all of these. Everybody okay with that? All right, I'm going to pause for a second and just talk about this expression because we need to reevaluate this. 1/2 is 1/2 times 1. Agreed? That's the first rectangle. Whereas 1 is 1/2 times 2. And 3/2 is 1/2 times 3. See how it's the rectangle number times the width every time? So we just advance another width, don't we? Okay? All right. 2a, if you're finding the area of 8 rectangles, we're going to bound from 3 to 4, 3 to 4. What's the width of each rectangle? Talk to your peers. Go. 5, 4, 3, 2, 1. What is the width of each rectangle? So you took 4 minus 3 and you divided by 8 to get 1/8. Agreed? Okay, good. Now notice we're going from 3 to 4. 3 to 4, we're not starting at 0. See if you can determine, and you could write it multiple different ways. You could use a mixed number, you could use a fraction, however you want to. But if you're finding the area of those 8 rectangles, at what x value, so what are these spots where you evaluate the heights? Take a good 2 minutes and talk with your peers. See if you can come up with the spots where you evaluate those heights. Go. Okay, eyes up here. Let's see what we got. This is where we're really going to start transitioning. So you really got to focus here. Do I evaluate the first height at 3? No, you have to go over how much? 1/8. So the first spot is 3 and 1/8. Agreed? Or I would like to write it as 3 plus 1/8. You all good with that? And then the next spot would be 3 plus 2/8, right? Or a quarter. So I went over 1/8 times 2, because that's the second rectangle. And then the next one would be 3 plus 1/8 times 3. And then 3 plus 1/8 times 4. So you go over 1 width, 2 width, 3 width, 4 width. Do you see that? We go over another width every time. Now, I need more here. I'm not done yet, right? But your numbers should be 3 1/8, 3 2/8, 3 3/8, 3 4/8, 3 5/8, 6/8, 7/8, and finally 4 would be your last spot, right? So we want to transpose this so we now don't, so we're going to use a variable, okay? Suppose you're finding the area under x squared from, we're going to go 3 to 5. You're finding the area of n rectangles. What's going to be the width of each rectangle? Talk to your peers. Go. And stop. Okay, what do you got? 2 over n. Very good. You took 5 minus 3 and divided by n. So the answer is 2 over n. Extremely important that everybody understands why I got 2 over n. We good? Okay, now let's do this together. It says if you're finding the area of n rectangles, at what x values do you evaluate the heights? Where are we starting? What's our starting spot? 3, but we don't do it at 3, do we? We have to advance 1 width, don't we? What's going to be the spot of that first spot then? We're going to do 3 plus 2 over n, right? And then the next spot is going to be 3 plus 2 over n times 2. So this is times 1. That'll be times 2, right? And then the next spot will be 3 plus 2 over n times 3, so on and so forth, right? We're going to continue to advance another width every time, aren't we? So the important thing that we just determined to try to finish what we wrote up top, is everybody okay with that? I'll leave it for a second. Because this is the big piece that we've got to add, and this is what you have to let sink into your mind. The first one won't be that big of a deal, but the second one will be a little bit bigger for you. Okay? Delta X is the width. And what did you do to calculate the width? You did B minus A divided by N. You took the last part of the interval minus the first part of the interval, and you divided by the number of rectangles. That's how you calculate the width of each rectangle. That should seem pretty clear to everybody, yes? Okay, and then the spot where we evaluate the heights, x sub I, that's equal to, what we did is we took, look at this last one, we took the starting point, and then we kept on adding widths to it, didn't we? So we take the starting point, and in this situation, what's the starting point? A, and then we added widths to it. So I'm going to say delta x times I. I refers to the rectangle number. So it might be rectangle 1, 2, 3, 4, 5. So this is the culmination of the piece that we need to be able to use. I mean, come on. For a moment there, like as you look at that, you're like, I must be pretty smart if I'm dealing with that now, right? Like you take your homework home and mom and dad say, like, you're going to Harvard, right? Because that looks absolute gibberish. Let us complete it. You are going to add up the area of an infinite number of rectangles. You're going to do something that most people that you ever encounter will have never done before. And to you, that may not seem like a big deal. I'm going to ask right now, anybody replaced a head gasket on a truck? The two of us. Not an easy job, is it? I'm pretty proud I've done it. Are you proud? Yeah. It's cool to walk those paths that other people haven't done before, right? Okay? Same way, you guys can accomplish something that most people haven't done. Let's do it. We're going to find the area under x squared from 0 to 2. I'm not going to evaluate. I am simply going to start by just drawing the picture. I've changed this up just a little bit. X squared looks like that. I'm going to find the area from 0 all the way to 2. There is no more estimating. It is exact today. It is exact. Every time you find the area, you should start with finding the width of each rectangle. What's our formula to find the width of the rectangle? B minus A over N. That will give us delta X. So what is B minus A? It is 2 minus 0, which is 2. So we get 2 over N. Is everybody clear how I came up with 2 over N? By the way, you're going to have to do this on the test. Okay, so what we take you through, it's going to seem like a lot today. You're going to get better at, but you have to do this on a test. For what x values do we evaluate the sum? Well, we say that x of I, we said, was equal to A plus delta x I. Now, that looks like garbage right now. We're going to make it look pretty simple. Yes, Kenny? That was intentional because the other day I called Kenny Easton. And I was seeing which one felt more offended. What up, dog? What?
Scroll up.
Scroll up, yeah.
Oh, okay, that didn't. Too hard.
By the reaction, he was slightly more offended.
Doesn't Kenny sit right here?
I
can't remember when I was.
Kenny used to sit right here. I did move him second semester. I can't remember. All right. So, watch how easy this becomes, you guys. I get, what is your A value? 0 plus, what is the width? 2 over n times I will just be 2i over n. And what's 0 plus 2i over n? Just 2i over n. So that's not tough, is it? I refers to the rectangle number. So it's first rectangle, second rectangle, third rectangle, fourth rectangle, so on and so forth. Okay? All right. Now, express the definite integral as an infinite limit. Definite integral. On the bottom goes our start. Where are we starting? To what? 2 of the function. What's the function? X squared is what we're using, and you write dx. That means the area underneath the curve. Everybody good with that? That is equal to the limit of a Riemann sum. Limit as n goes to infinity of the sum from I equals 1. I equals 1. We start with the first rectangle. We go to n number of rectangles, and what are we pushing n to? So we're going to start with 1. We're going to go to infinity. We're actually adding up an infinite number of rectangles. Okay.
Is this how we get like the exact answer?
Yes. Yes.
I have a question.
Yes.
So you know how like you have I don't know like that squiggly thing. I mean.
This thing?
Yeah.
Yeah.
That what does it mean again?
It's the definite integral. It means the area bounded underneath the curve.
Okay. So is all of that like the limit stuff? Is that
Kind of. That this kind of limit stuff means kind of that thing.
Or it's like
Yeah.
the same equation, or are both sides like equal to each other?
They're equal to each other. It means the sum. Means sum. Okay, so this next piece is f of x sub I. So we don't write f of x sub I. What we write is the function with x sub I plugged into it. So what is our x sub I value? So we're going to take that and plug it in for x squared. So 2I over n quantity squared.
So what we got through on this is what we plug in for n.
Yep. And then the final part is times delta x. What is delta x?
2 over n.
Times 2 over n. No. This is what we do by hand.
Oh, okay. Anywhere adjust.
We will.
Does that mean it'll be negative 4 over n?
No. Okay. So you see the left side, we want to compute the right side. And the right side, so far we have the limit. This will be easy for you as we start. As n goes to infinity of the sum from I equals 1 to n. This is not I as in an imaginary term. Okay, this is not like the square root of negative 1. This is I as just a variable. So what do you get if you square that? 4i squared over n squared times 2 over n. Well, I can multiply that, can't I?
Yeah.
I get the limit as n goes to infinity of the sum from I equals 1 to n of what's on the top? 8i squared over n cubed. And third. Everybody follow me?
I don't know what that was.
Now what I'm going to do is I'm going to do something that's going to make you slightly uncomfortable. I'm going to factor everything out except for the I portion. So I'm going to write it the limit as n goes to infinity of 8 over n cubed times the sum from I equals 1 to n of I squared. So all I did is write the 8 over n cubed out front. I'm going to pause and let you do that because we need to transition. Nope.
Yeah, I know it's not. I know why we can do this, but it doesn't seem like we should. Why can we just take the
That's just a property with sums that you're allowed to do. So okay, I'll give the answer. So 3 plus 6 plus 9 plus 12. If you were to do that, that's the same thing as 3 times 1 plus 2 plus 3 plus 4. That's basically what we did there is we factored that thing out, just like we did for the 3. That's what we just did. Ella? Shh, folks. Shh.
Is that supposed to be under F, or is it just there because you didn't have enough room? Like, should I write that under?
You can write it under there. I didn't have enough room, but now we are going to substitute the known sum. Okay? Yep. Okay, at this point we need to digress. Okay? You can kind of just set down your pencil, and we want to make the next step, but the fact is, if I tell you what the next step is, you're going to get angry and upset. You're going to be like, how come this makes absolutely no sense? Okay? You ready? So we got to press pause. Do you remember this from last year? And some of you won't. I apologize, but 1 plus 2 plus 3 plus ... plus 98 plus 99 plus 100. Do you remember that? And we said this great guy named Gauss, he came along and he found out how to do that sum in like 2nd grade rather quickly. Do you remember how he did that?
No. It's something with N plus 1.
They all had 101, right? And how many are there? There's 50 of them. So we got 5,050. That's what it adds up to, right? It was really, really smart. And so Gauss had this great thing. He said if you add up the numbers starting with 1 to whatever you want, all you have to do is take 1 plus n, the first number plus the last number, and then there are half the number of groups. See what I'm saying? I'm sorry, this isn't quite right. It's close. So if we do that, we get n times n plus 1 divided by 2. And we actually, last year, we proved those things. Do you remember when we did something called math induction? And I said, show true for the first few cases. Case 1, 2, 3. Remember that? Remember that the second thing was that you assumed true for case n equals k. We called that our inductive hypothesis. And you remember the last step, we had to prove it was true for case n equals k plus 1. And we did that proof. You ended school that day, right? And we came up with some formulas. Here's the deal. You don't need to do this again. The first time I taught this class here, the kids had never seen math induction. So at this point I said, oh, shoot. So we pressed pause. We did 3 days of just math induction, and we got back to it. But you've already seen the math induction, right?
Yeah.
Do you remember it?
Yeah.
We don't have to go through remember it, but can we just write down the formulas that we got from it and make use of them?
Yeah.
So then find a spot where you got blank paper where you can write these down and never lose them.
How many are there?
There's 4. Back page of your notes, it looks like. And yes, we will just get through 1 problem today. Tomorrow we'll get through 2, and Friday we'll get through 1 more. But it's a slow go at it. So you'll be able to finish up your work from trapezoidal and midpoint stuff tonight. We just want to get through 1. Tomorrow it's going to go quicker, trust me. So the sum from I equals 1 to n of I is simply equal to n times n plus 1 divided by 2. And if you're wondering why, I say we proved it using math induction. It's been proved. Suppose you're trying to add up the first number of squares, I squared. So for example, 1 plus 4 plus 9 plus 16 plus ... Suppose you're trying to add up those. Well, we proved that last year as well, and it came out to n times n plus 1 times 2n plus 1, all divided by 6. If you can't tell, I'm doing these from memory, and I'm worried I forget it. I don't know, I'm worried. We're going to do another one, n, the sum from I equals 1 to n of I cubed. Suppose you're adding up the first cubes. Actually works out really cool. As you add up the cubes, you get n squared times n plus 1 squared all over 4. Does that look familiar to anybody? Isn't that the same thing as that, just squared, right? It just so works out. It's the same as that thing squared. And then the last thing we have is this. The sum from I equals 1 to n of a constant. So suppose that you're just adding up the number 4. I'm going to add up the number 4 5 times. If I add up the number 4 5 times, what does it add to? 20, right? You just take the number and you multiply it by the number of times you're adding it up. So if you just get a constant, it is simply the constant times the number of times you're adding it up. Those are your 4 formulas that you need. Got it referenced somewhere?
Yeah.
Okay, let's flip back and make use of it and finish this problem off. Here we go. I've got the limit as n goes to infinity of 8 over n cubed. And I don't want to use this something of I squared anymore. Did we learn a formula you can plug in that place? We did. What's that formula?
N times n plus 1 times n 2n plus 1 all 6.
That's the formula. Now, some of you are like, so what, Mr. Gintz? Like, what did we just do? Here's the amazing thing, folks. Look, we got rid of I altogether. Now we only have the variable n, and we're trying to determine an infinite limit. Have we ever done infinite limits before? Amen, we have, right? And it was easy peasy. So let's do it. We've already done this. This is like review. Limit as n goes to infinity. And I'm going to start multiplying this stuff out. Can we do that? Yeah. Okay, so 2n times n, 2n squared times n will be 2n cubed times 8 will be 16n cubed. All right, now let's do this part. 1 times 2n and 1 times n. Everybody agree you'll get 3n for the middle? And 3n times n is 3n squared times 8, 24n squared. Yes.
How do you know what's that formula, like the n with the divided?
Because I've got the squared one, so when you look back at what we wrote down, you're looking for the one with the I squared term right here. See that? Okay, good. All right, and now let's do the last part here. Now I multiply the last terms. 1 times 1 is times n times 8, 8n. So we multiply it out the top. If you struggle with that multiplication process, maybe you need to write it out further. What do I get in the bottom? 6n cubed. Sweet. We know how to find that infinite limit. What should I factor out of the top? What's the biggest term I can take out of the top? We don't even have to worry about the constant. We could just worry about the variable. I'm going to take out the n cubed. Okay? So I have the limit as n goes to infinity of, I factor out an n cubed out of the top. What are you left with?
You have 16 plus 24 over n plus 8 over n squared.
Good. So Easton sees I've got this 16 guy here. This one's going to be 24, but because it's only an n squared, it's going to be over n. And then because this only has an n, it's going to be 8 over n squared. Okay? Does everybody remember that from when we did that together? Yeah. And then on the bottom, what do you factor out? You factor out n cubed times 6. What's going to happen? N cubes are gone. As n goes to infinity, these go to 0. So you're left with
1.
16 over 6, which is 8/3, otherwise known as 2.6 repeating. That is the exact value. There's no more estimation. You literally took rectangles of an infinitesimal width and added up the area of an infinite number of them. You did this crazy business of 0 times infinity, and what does it equal? It equals 8/3 in this situation, folks. If that doesn't blow your mind, then I guess I don't know what to do. Take out your calculator, and I'm going to show you something that you love. Go to y equals. So you just retype it. It's fine. Yeah. Then that'll be part of your learning because you have to do that for the test anyway, right? Okay. So everybody, you're going to want to do this. Trust me, you're going to want to do this. So I start here. I've got y sub 1, and I'm going to type in its place for y sub 1. I'm going to type in x squared because that's our function. Go zoom standard, zoom 6, so we can all see the same thing. And I'm going to calculate the area to check my answer. What can I press on my calculator? Second, calculate. We've learned how to use all of these except for one, haven't we?
7.
Doesn't 7 look familiar now? Yeah, we press number 7, and it asks you to state the lower limit. That's where you start. Where do we start? 0, and where do we end? We said to end at 2. Press enter. And your calculator does that. Then select 7. 0. Press 0. That's where you start. Well, you want to type in the number 0. Yeah, so you want to look at your graph. You want to second calculate. Number 7. Lower limit is 0. Upper limit is 2. See that?
And then you wrote that. That's much faster.
Well, you could check your answer, but that's that. Okay, so folks, where could you start? If you look at your next worksheet, you could start by looking at the first 2. Okay? The first 2. There's a total of 8 problems, so over the course of the next 3 days, we want to be able to feel like we can handle these 8 problems. Now, that was a big introduction. It usually takes a long time. That is a grand total of 33 minutes. Tomorrow, each problem, we'll be able to do each problem in it'll take about 8 minutes. It's going to be a lot shorter. So we're going to be a little bit quicker, okay? Good job.